Ever get that feeling like when you're trying to learn something new, maybe for a project at work, maybe just because you're curious about something,
Yeah.
and you just wish you could skip ahead to the good parts,
To the
Yeah,
nuggets.
no, the stuff that really matters. Like, imagine having like a whole library of information,
Right.
and someone distilled it down to just the key insights, just for you.
That's the dream, right? Like efficient understanding without all the waiting.
Exactly. And
Yeah.
that is precisely what we're doing right here, right now.
Oh, wow. Pressure's on.
We are taking a deep dive into a subject. We're going to sift through all the detail,
What a nitty-gritty.
and we're going to resurface with the essential knowledge that you need, your shortcut to being well-informed. And today, we are diving into the world of square numbers and square roots.
Ooh, squares and square roots. Sounds kind of mathy.
It is mathy, but I promise you, we've gone through the material, we've extracted the most important concepts, the interesting patterns, maybe even a few surprises.
Ooh, I like surprises.
Right. All without overwhelming you with, too much complexity.
All right, I'm in. I'm ready to be surprised.
Okay, great. So our mission here is to make these really fundamental mathematical ideas crystal clear and, dare I say, even a little bit fun.
Fun math. All right, you've got my attention.
Okay, so let's start at the very beginning. What exactly is a square number? So think about a square, the shape. Let's say one side of that square measures, I don't know, 4 centimeters. How would you calculate the area of that square?
Well, you just multiply the length of one side by itself, right? So 4 centimeters times 4 centimeters would give you 16 square centimeters.
Exactly.
Yeah.
And that 16, that's our square number. It's what you get when you square the side length. And the source material that we're looking at today, it actually gives us a really nice table to kind of illustrate this.
Okay.
So if you have a side of 1 centimeter, the area is 1 square centimeter, which is 1 squared. If you have a side of 2 centimeters, the area is 4 square centimeters, 2 squared. And it goes on like that, 3, 5, 8. They even use like a general side length 8, so the area would be a squared.
So basically, we're talking about multiplying a number by itself to get a square number.
That's it. You got it. So
Yeah.
mathematically speaking, a square number is any natural number, let's call it
Okay.
that can be expressed as another natural number, n, multiplied by itself, or n squared.
Okay, so equals n squared. That's our formula.
Exactly. Now, I love how the source material, it just kind of jumps right in and poses a question to the learner. It says,
I like this.
is 32 a square number?
Is 32 a square number? Let me think. Well, 5 squared is 25.
Okay.
6 squared is 36.
Right.
So 32 falls somewhere in between. So is there any whole number between 5 and 6 that when you multiply it by itself, you get 32?
Nope, there's not.
Not a whole number, no?
No. And, just a quick reminder, natural numbers, those are the counting numbers, 1, 2, 3, and so
Right.
on. So 32, it doesn't fit our definition. So it's not a perfect square.
Okay.
And that actually introduces us to another term that you might hear when you're talking about square numbers.
Okay.
And that is perfect squares.
Perfect squares.
And they're really just another way of referring to square numbers.
So like synonymous, basically.
Exactly.
Gotcha.
So, numbers like 1, 4, 9, 16, 25, those are all perfect squares because they can be obtained by squaring a natural number.
All right, makes sense.
Now, to get you thinking a little bit more actively about this, let's try a little challenge here. And this is inspired by our source material.
Hit me.
Find the perfect square numbers that lie between 30 and 40.
Okay.
And we'll do another one between 50 and 60.
Okay, so between 30 and 40, the only perfect square, I think, is 36.
Good.
Which is 6 times 6.
Exactly.
And then between 50 and 60, ooh, that's tricky. 7 squared is 49, and 8 squared is 64. So there aren't any perfect squares in that range.
Well done. You are 2 for 2.
2 for 2. All right.
Okay, so we've established what square numbers are.
Yes.
Now let's look at some of their interesting characteristics, or what our source material calls properties of square numbers.
Properties. I like it. It's like they have personality.
They do.
Okay.
So our material gives us a table with squares of numbers from 1 to 20.
Right.
And did you notice anything interesting about the digit in the units place?
Units place. You mean like the last digit?
Yeah, the last digit of those square numbers.
Let me see. The last digit. Well, it seems like there's only a limited set of possibilities, right?
Yeah.
They only ever end in 0, 1, 4, 5, 6, or 9. You never see a square number ending in 2, 3, 7, or 8.
That is a great observation. Why do you think that is?
Well, if you think about it, when you multiply any single digit number 0 through 9 by itself, the last digit of the result will always be one of those 6 we just talked about.
That is exactly right.
So it's all about the units digit of the original number.
Right. It's like a little built-in shortcut.
Yeah, a little cheat sheet.
If you see a number ending in, 2, 3, 7, or 8, right away, it can't be a perfect square.
You can just dismiss it.
Yeah. So let's put this knowledge to the test, okay? Our source material gives us this great question. Can you determine whether the following numbers are perfect squares just by looking at their units digit? All right, so you ready for the numbers?
Yeah.
Okay. 1057, 23453, 7928, 2222222, 1069, and 2061.
All right, let's analyze these. Okay, so 1057 ends in a 7, so it cannot be a perfect square.
Correct.
23453 ends in a 3, also not a perfect square. 7928, it ends in an 8, so that's a definite no. 2222222 ends in a 2, so it can't be a perfect square either. Now, 169 ends in a 9, which is a possible ending for a perfect square, so I can't rule that one out just yet. And 2061 also ends in a 1, which is also a potential ending digit, so we need more information for those last 2.
Exactly right. It's like a first-pass filter.
Yeah, eliminate some of them right away.
Yeah. So, and this leads to another challenge that I think you'll enjoy. Can you list 5 numbers that you can immediately identify as not being square numbers just by looking at that units digit? And then can you list 5 numbers where the units digit alone doesn't give you enough information?
Okay, so for the first category, I can just pick any numbers ending in 2, 3, 7, or 8, right?
Right.
Okay, so how about 12, 53, 87, 198, and let's throw in 2023.
Okay, good. And what about for the second category?
For those, I need numbers ending in 0, 1, 4, 5, 6, or 9. They could be squares, they might not be. So let's go with 10, 21, 34, 45, 56, and 69 for good measure.
Perfect. All right, let's go a little deeper into these ending digits, okay? Our material includes a table, they call it Table 1, and it shows the squares of numbers from 1 to 50.
Okay.
So if we look at the square numbers that end in the digit 1, like 181, 121, 361, 441,
Right.
What do you notice about the original numbers, the numbers being squared? Like, what digit do those end in?
Let's see. So 1 squared is 1, 9 squared is 81, 11 squared is 121, 19 squared is 361, and 21 squared is 441. So it looks like they all end in either 1 or 9.
Exactly right. So there's a pattern there.
There is.
And then the material asks, which of the following numbers would have a square ending with the digit 1?
Okay.
1232, 772, 822, 1612, and 1092.
So we're looking for ones that end in 1 or 9, right?
Yes.
Well, none of those do. They all end in 2, so none of their squares will end in 1.
Exactly. They were trying to trick us with that one.
Sneaky.
Okay, how about square numbers that end in 6? Our source material gives examples like 16, 36, 196, 256. What do the numbers being squared end in this time?
All right, let's look at the units digit again. So we have 4 squared is 16, 6 squared is 36, 14 squared is 196, and 16 squared is 256. So it seems like they end in either 4 or 6.
There it is. Another pattern.
Another pattern, boom.
And of course, another question. Which of the following numbers would have the digit 6 in the unit place of their square?
Okay.
19 squared, 24 squared, 26 squared, 36 squared, and 34 squared.
All right, let's examine these one by one, looking at that units digit. 19 ends in a 9, and we know 9 squared ends in a 1, so not that one. 24 ends in a 4, and 4 squared ends in a 6, so that's 1. 26 ends in a 6, and 6 squared also ends in a 6, so that's 2. 36 ends in a 6, its square also ends in a 6, that's 3. And 34 ends in a 4, 4 squared ends in a 6, that's 4. So our answer is 24 squared, 26 squared, 36 squared, and 34 squared.
Wow, you're on a roll.
I'm getting the hang of this.
There's one last question in this section. What will be the, and they put it in quotes, 1's digit, which is the same as the units digit in the square of the following numbers: 1, 2, 3, 4, 2, 6, 3, 8, 7, 5, 2, 6, 9, 8, 9, 9, 8, 8, 8, 2, 2, 1, 2, 2, 2, and 9, 1, 0, 6.
All right, so we just need to focus on that last digit of each number and square it, right?
Right.
Okay, so 1, 2, 6, 3, 87 ends in a 7, so 7 squared is 49, units digit is a 9. 5, 2, 6, 9, 8 ends in an 8. 8 squared is 64, units digit is a 4. 9998 80 ends in an 8. 8 squared is 64, units digit is a 4. 9996 ends in a 6. 6 squared is 36, units digit is a 6.
Boom. You nailed it. Okay, let's switch gears a little bit and think about zeros.
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 Okay.
So our source material gives us some examples here, like 10 squared is 100, 20 squared is 400, 80 squared is 6,400, and so on. What pattern do you see when you compare the number of zeros at the end of the original number to the number of zeros at the end of its square?
Well, it seems pretty straightforward, right? The number of zeros at the end doubles. So 1 0 becomes 2 zeros, 2 zeros become 4 zeros, and so on. Which also means a perfect square can only have an even number of zeros at the end, right?
That is a key insight. A perfect square can never have an odd number of zeros at the end.
Nope.
So like 3,000, we know right away that can't be a perfect square.
Exactly. Zeros are giving away the secret.
So the material asks, if a number ends with 3 zeros, how many zeros will its square have?
It would have 6 zeros. 3 doubled is 6.
Exactly. Okay, quick check. How many zeros will be at the end of the square of 60?
60 squared is 3,600, so 2 zeros.
Good. And for the square of 400?
4 zeros. 400 squared is 160,000.
You got it. Okay, let's think about even and odd numbers for a second.
Even and odd.
If you square an even number, what do you get, even or odd? What about squaring an odd number? You can look back at that table 1 we talked about earlier, if that helps.
Yeah, looking at the table, it's pretty clear. The square of an even number is always even, and the square of an odd number is always odd. It's like they stick to their own kind.
They do, and it makes sense mathematically, right? Even times even will always have a factor of 2, so it has to be even.
Right.
And odd times odd, it can never have a factor of 2, so it stays odd.
Makes sense.
So the material gives us another question. They give us some numbers, and they ask, for the following numbers, would their square be odd or even, and why? The numbers are 727, 158, 269, and 1980.
All right, so 727, that's an odd number, so its square would be odd. 158 is even, so even squared. 269 is odd, odd squared. 1980 is even squared. And the y is really just based on whether the original number is even or odd.
Exactly. All right, we've covered some fundamental properties. Now, get ready for this, because we're about to explore some more interesting patterns, and our source material is really excited about these.
Ooh, interesting patterns. I'm intrigued.
The first one involves adding triangular numbers.
Triangular numbers.
Yeah, triangular numbers. So just a quick reminder for anyone who might not remember.
Yeah, refresh my memory.
What exactly are triangular numbers?
Triangular numbers are a sequence of numbers that can be visualized as, well, triangles made of dots. So you start with 1 dot, then 3 dots in a triangle shape, then 6 dots, 10 dots, and so on. You get them by adding consecutive natural numbers.
Okay, so what's the connection to square numbers?
Well, here's the cool part. If you add any 2 consecutive triangular numbers together, you always get a perfect square.
It's true.
It's like magic. The source material even gives us some examples. 1 plus 3, which is 4, which is 2 squared. 3 plus 6 equals 9, that's 3 squared. And 6 plus 10, which is 4 squared. You can actually picture this if you imagine arranging those dots.
Right. You can put the 2 triangles together and form a square.
Exactly. Triangles and squares working together in harmony.
All right, next up we have numbers between square numbers.
Numbers between square numbers.
Okay, so let's look at the sequence of squares. 1, 4, 9, 16, 25. How many non-square natural numbers are there between 1 and 4?
Let's see. Between 1 and 4, we have 2 and 3. So 2.
Okay, how about between 4 and 9?
5, 6, 7, 8. So 4.
And between 9 and 16?
10, 11, 12, 13, 14, 15. That's 6.
Do you notice a pattern in those numbers?
2, 4, 6. It seems like it's increasing by 2 each time.
It is. And our source material is kind enough to give us the general rule. Between n squared and n plus 1 squared, there are always 2 non-perfect square numbers.
So between, say, 10 squared and 11 squared, there would be 20 non-square numbers.
You got it.
That's pretty neat. A nice, concise rule.
Yeah, it's elegant.
Elegant math.
So naturally, they give us a couple questions to test our understanding.
Okay, bring it on.
How many natural numbers lie between 9 squared and 10 squared?
So n is 9 in this case, so 2 times 9 is 18. 18 non-square numbers.
And how about between 11 squared and 12 squared?
N is 11. 2 times 11 is 22. 22 non-square numbers.
Okay, and another one, a little bit trickier. How many non-square numbers lie between 100 squared and 101 squared?
Okay, so n is 100. 2 times 100 is 200. 200 non-square numbers.
Okay, how about between 90 squared and 91 squared?
N is 90. 2 times 90 is 180. 180 non-square numbers.
Last one. Between 1,000 squared and 1,001 squared.
Okay, so n is 1,000. 2 times 1,000 is 2,000. 2,000 non-square numbers.
See, once you get that pattern,
It's a piece of cake.
it's easy. All right, the next pattern is called adding odd numbers.
Adding odd numbers, okay?
And this one, it's pretty cool. So let's start with the first odd natural number, which is 1.
Okay, 1.
That's equal to 1 squared, right?
Right. 1 times 1 is 1.
Now take the sum of the first 2 odd natural numbers. 1 plus 3. What do you get?
1 plus 3 is 4, which is 2 squared.
Exactly. Okay, now the sum of the first 3 odd natural numbers. 1 plus 3 plus 5.
That's 9, which is 3 squared. Oh, I see where this is going.
Do you see the pattern?
Yeah, the sum of the first and odd natural numbers is always equal to n squared. That's a beautiful connection.
Isn't it? It's a really elegant mathematical truth.
I love those aha moments in math.
Me too. And what's cool is the reverse is also true. If a number is a square number, It must be the sum of consecutive odd numbers starting from 1.
So it works both ways.
Yeah, and our source material actually shows a really neat way to use this to check if a number is a perfect square.
Oh, how do you do that?
You just start subtracting consecutive odd numbers starting with 1. And if you reach 0 after subtracting, say, n odd numbers, then that original number wasn't squared. They use 25 as an example.
Okay, so 25 minus 1 is 24, minus 3 is 21, minus 5 is 16, minus 7 is 9, minus 9 is 0. That's 5 odd numbers, and 25 is indeed 5 squared.
I like this method. It's very visual.
It is. And they also give an example with 38 to show what happens when the number isn't a perfect square.
Yeah, you'll end up with some weird remainder that's not the next odd number in the sequence. Right. And of course, we have a question for you to try. Using this repeated subtraction method, determine whether the following numbers are perfect squares or not, and if they are, find their square root: 121, 55, 81, 49, and 69.
Well, we actually already did this for some of these earlier, right?
We did.
Yeah, we found that 121 is a perfect square. Its square root is 11. 49 is also a perfect square. Its square root is 7. And 55 is not a perfect square, so we just need to check 81 and 69. Okay, so for 81, we have 81 minus 1 is 80, minus 3 is 77, and so on. After 9 subtractions, I get to 17 minus 17 equals 0. So 81 is a perfect square. Its square root is 9. Now for 69, 69 minus 1 is 68, minus 3 is 65, and I keep going, but I end up with 5 minus 17 equals negative 12. Didn't reach 0, so 69 is not a perfect square.
Fantastic. Okay, next pattern is the sum of consecutive natural numbers. This one specifically focuses on the squares of odd numbers.
Okay, odd squares. I'm listening.
So let's take 3 squared, which is 9. Now notice that you can write 9 as the sum of 2 consecutive integers, 4 plus 5.
Right.
Okay, how about 5 squared, which is 25?
25 is 12 plus 13. Ooh, consecutive again.
And 7 squared is 49.
Which is 24 plus 25. I'm seeing a pattern here.
What's the pattern?
It seems like the square of any odd number can be expressed as the sum of 2 consecutive positive integers.
Exactly right. And, the source material gives us a nice general way to represent this.
Okay.
They say that for any odd number, n squared is equal to, in parentheses, n squared minus 1, close parentheses, divided by 2, plus, in parentheses, n squared plus 1, close parentheses, divided by 2. And those two terms, those will always be consecutive integers.
Ah, that's a clever way to show it algebraically.
Isn't it?
All right, I'm ready for a challenge.
Okay, good. Express the following squares as the sum of 2 consecutive integers: 21 squared, 13 squared, 11 squared, and 19 squared.
Okay, challenge accepted. 21 squared is 441. Using that formula, 441 minus 1 divided by 2 is 220, and 441 plus 1 divided by 2 is 221. So 441 is 220 plus 221. 13 squared is 169. 169 minus 1 divided by 2 is 84, and 169 plus 1 divided by 2 is 85. So 169 is 84 plus 85. 11 squared is 121. 121 minus 1 divided by 2 is 60, and 121 plus 1 divided by 2 is 61. So 121 is 60 plus 61. And finally, 19 squared is 361. 361 minus 1 divided by 2 is 180, and 361 plus 1 divided by 2 is 181, so 361 is 180 plus 181.
You are amazing. That was a lot of calculations.
I'm getting my mental workout in today.
Me too. Okay, so the material gives us a kind of a reverse question.
Okay.
They say, is the sum of any 2 consecutive positive integers always a perfect square?
I don't think so. Like if you take 2 and 3, their sum is 5, which isn't a perfect square.
Right.
Or 7 plus 8 is 15, also not a perfect square. So it seems like it only works one way. Every odd square can be expressed as the sum of 2 consecutive integers, but not the other way around.
That is a great point of clarification.
Okay.
Okay, let's move on to our next pattern. Product of 2 consecutive even or odd natural numbers.
Product. So we're multiplying now.
We are multiplying. And this reveals a pretty cool relationship.
Okay.
So think about the product of 11 and 13. Notice that 12 sits right in the middle of them.
Right in between.
So we could think of 11 as 12 minus 1, and we could think of 13 as 12 plus 1.
I see where you're going with this.
So if you multiply it, like generally speaking, a minus 1 times a plus 1, what do you get?
Ah, that's the difference of squares pattern. You get a squared minus 1.
Exactly. So in our example with 11 times 13, that's the same as 12 squared minus 1, which is 144 minus 1, or 143.
Cool.
In our source material, they give us more examples. They say 13 times 15, that's 14 squared minus 1.
Which is 195.
29 times 31 is 30 squared minus 1.
899.
And 44 times 46 is 45 squared minus 1.
2024. Wow, that's a handy pattern to know.
It is. So there's a question here. It says, can we find the square of the following numbers using this pattern?
That's
And the
fast.
numbers are 101, 101, 11 squared, and a little 101, 101, 11 squared.
That's interesting. It seems like the pattern we just talked about is more about finding the product of 2 numbers that are 1 less and 1 more than a certain number, resulting in that number squared minus 1. It doesn't directly tell us how to find the square of a single number, like 11, 11, 11, 11. I wonder if this question might be meant for a different pattern, or maybe it's slightly off.
That's a very sharp observation. And I think you might be right because those numbers actually fit perfectly with the next set of patterns that we're going to look at.
Oh, good. So they didn't make a mistake.
Not a mistake, just maybe misplaced it a little bit.
All right, let's see these next patterns then.
Okay. These are what the material calls more patterns in square numbers. They even put more in all caps.
Wow, they must be really excited about these.
They are. And these patterns, they're just really cool observations. And we might not get into the deep why they happen, but they really highlight the beauty of math, like how everything is connected.
But I love that about math. It's like a secret code.
It is. Okay, so first, look at the squares of numbers consisting only of the digit 1.
Only ones.
So 1 squared is 1, that's easy. 11 squared is 121.
Okay.
111 squared is 1, 2, 3, 21.
Oh, I see where this is going.
1111 squared is 1, 2, 3, 4, 3, 2, 2, 1.
It's a palindrome. And it just keeps growing with the number of ones.
Right. It's symmetrical.
And now those questions about 11 on 11, 11 squared and 11 on 11, 11 squared make sense.
They do. So following the pattern, what would 11, 11, 11 squared be?
That would be 1, 2, 3, 4, 5, 6, 5, 4, 3, 2, 1.
And 111, 11 squared.
1, 2, 3, 4, 5, 6, 6, 5, 4, 3, 2, 1. It's like a numerical pyramid, growing up and then back down.
It is. Okay, now for another cool one. Look at numbers that are a sequence of 6s followed by a 7.
Okay, 6s and a 7.
So we have 7 squared, which is 49. 67 squared is 44,889. 6667 squared is 444,889.
I'm already seeing the pattern.
What's the pattern?
Okay, so if you have a number with, let's say, n6s followed by a 7, the square starts with n4s, then an 8, then an 8s, and it ends with a 9.
You got it.
Okay.
And wouldn't you know it, they ask us to find the square of 6666667 and 666666667 using this pattern.
All right, let's do it. So for 6666667, that's 6 6s and a 7. So we should have 6 4s and 8 6 8s and a 9. That gives us 4 4 4 4 4 4 4 8 8 8 8 9.
And for 666666667.
7 6s and a 7. So 7 4s and 8 7 8s and a 9. That makes 4 4 4 4 4 4 4 8 8 8 8 8 8 9. I feel like a code breaker.
You are. These patterns are just incredible.
Yes, right.